Hey, what's up, everybody? It's your boy Proftrof, and we are back again with another Island Biosphere video. This is part 6, the open plains. So we're probably in this video we're gonna evolve into mammals and shit, right? Last video was we reached the dry land. We started developing some, more advanced species. So let's see where biology takes us this time.
Last time, we saw the development of the first terrestrial ecosystems within the vast humid forests that cover the supercontinent, supported by a warm, wet climate of unceasing rain and storms. But it's only a matter of time before these stable, benign conditions begin to change. As the forests fill the atmosphere with oxygen, they'll simultaneously take in enormous amounts of carbon dioxide and hydrogen sulfide. Thus far, the levels of these gases have been maintained by the aerobic respiration of animals and by the activities of sulfur-metabolizing microbes respectively, but the globe-spanning forests may deplete these gases faster than they can be replenished. On top of that, as the mountains are eroded by acid rain, the newly exposed rock reacts with the carbon dioxide to form calcites, further lowering atmospheric CO2 levels. Since carbon dioxide is a greenhouse gas, a decrease in its abundance will lead to an overall cooling of the planet's climate. The enormous storms that deliver rain to the center of the supercontinent rely on high oceanic temperatures, and even a drop of only a few degrees will be enough to disrupt weather patterns. Add in that lowered hydrogen sulfide levels slow the formation of sulfuric storm clouds in the upper atmosphere, and the production of the hypercanes that have fueled the growth of the global forests will come to a halt, and the inland regions of the supercontinent.
Oh yeah, he never mentioned that, but with the way he was evolving everything on the land, he never mentioned what sort of evolutionary traits the animals, I guess, or the species would get from the weather. Like it's cold or is it hot on this planet? What's up and what would they do, right? Because like you need to survive in that environment. He never mentioned that.
Will be
Interesting.
starved of water, and
I
thus
wonder
the
if it's
forests will
purpose
dwindle,
or not.
giving way to vast tracts of open prairies and plains. And although the necrophytes and malacoforms will return a portion of the carbon and sulfur content of the tree's tissues to the atmosphere through decomposition, the remainder will become sequestered underground as the trees become fossilized, effectively removing them from the carbon and sulfur cycles, meaning the original atmospheric levels can't be recovered. Many species may not survive this environmental upheaval, and those that do will need to adapt to an entirely different world. Note, however, that due to the fact that this transition takes place quite gradually, the resulting decrease in biodiversity won't be significant enough for it to qualify as a full-blown mass extinction. But don't worry, we'll cover those in much more detail in a future episode. One of the most obvious changes in this new world will be in the vegetation. The once expansive forests will now only exist near the coasts and around lasting sources of fresh water, while in drier habitats the trees will be replaced by scrublands of mixed caulophite species. These plants, being significantly smaller than trees, don't require nearly as much water, carbon dioxide, and hydrogen sulfide, and so have an edge in the new climate. But they're also likely to strengthen their advantage with several important adaptations. All chemophytes have a central body, which in xenophytes is surrounded by a tough, waxy cuticle, and in xylophytes is strengthened by rigid support tissues. Unlike most plants on Earth, which grow gametangia from the tips of their branches, chemophytes' gametangia grow out from the main plant body. The leaves grow from a single meristem, or region of tissue growth, at the top of the plant to maximize their exposure to sunlight. However, if the meristem is damaged, either by being eaten or simply trampled, then the plant won't be able to grow new leaves and so will more than likely die. For a full-grown tree, this isn't a very prevalent danger because the meristem will be too high up to be within reach of any herbivore. But for smaller plants, the meristem is much more vulnerable. One clade of caulophite may solve this problem by having the meristem occur close to or even below the ground level, which can be achieved by shrinking the size of the plant body, with only the large prominent leaves emerging from the soil. Like all chemophytes, these new plants will be capable of asexual reproduction, which will let them spread very quickly across the newly opened habitats as the trees disappear, possibly forming huge clonal colonies in many areas. And when carrying out sexual reproduction in more densely populated habitats, the gametangia may grow out from the subterranean plant body into long stalks to maximize the dispersal of gametes. This clade of caulophytes, which I'll call brachyphytes, will become the dominant ground vegetation across the supercontinent, growing anywhere too dry for trees. These areas will be somewhat similar to grasslands on Earth, though since there's no actual grass, I'll refer to them using the more general term steppe. This new biome will cultivate a completely new assemblage of niches, which the recently evicted forest-dwelling species will furiously compete for. Among the lophostomes, the tiny malacoforms may survive the transition by dint of their extreme diversity and adaptability, but the diplostomes may be doomed to a much slower recovery, since they relied on the forests to maintain the high atmospheric oxygen levels they need to attain large sizes, and with the forests gone, oxygen levels will steadily fall, shrinking the diplostomes' maximum size and forcing them to surrender the megafaunal niches to the osteopods. The slow and bulky plecostricans may survive as small generalist grazers, relying on their sturdy shells for protection, and the desmostricans may maintain their lifestyle of dedicated malacivores. The elastospondylls, however, are specialized for life in the treetops, so as the forests disappear, they may be forced to explore new survival strategies. The elastospondyl's springy gladius lets them execute powerful jumps to pounce on prey as well as to leap between branches, which makes them a prime candidate for one particular development. On Earth, many arboreal species have independently evolved a membrane of skin, or patagium, that lets them glide from tree to tree, as seen in animals like flying squirrels, flying lizards, and even flying snakes. While there are some models that posit that gliding can evolve from a ground-dwelling ancestor, and while there are occasional oddities like flying fish and flying squid, the preponderance of arboreal gliders seems to indicate that the most common pathway to the
Bro, that thing is ugly as hell. Let's be honest, that thing is ugly as hell.
Evolution of a patagium is as a means of jumping between trees. The elastospondylls therefore seem very likely to evolve a patagium to augment their already powerful jumps, increasing the time they can remain airborne and the distance they can cover in a single bound, as well as to provide a degree of safety if they were to fall from a great height, acting like a parachute to slow their descent. To support a larger patagium, the middle pairs of limbs may become longer and broader, and outgrowths of the gladius may extend into the patagium to allow it to maintain its shape when outstretched, somewhat like the hyperextended ribs or ossified filaments found in many clades of living and extinct gliding reptiles. Altering the position of the limbs to influence the shape of the patagium may even allow them to manipulate their trajectory as they glide, and if this is the case, it seems very likely that one clade may take this development to its obvious culmination. While gliding has evolved over a dozen times in the history of life on Earth, powered flight, wherein the animal can remain airborne indefinitely, only has 4 known instances of having evolved. With the exception of insects, whose evolutionary path to flight isn't fully understood, wings have universally evolved from a patagium supported by an elongated and heavily muscled forelimb. But the elastospondyl's unique physiology may lead to them evolving a rather unorthodox method of flight. If the sites of major muscle attachment occur towards the posterior end of the animal to pull the gladius backwards, it may be more likely for the musculature necessary to power flight to develop around the 2 pairs of hind limbs, while the front 2 pairs of limbs provide stability and control pitch. As unusual as this method of flight is, there is some precedent for it in animals on Earth, as seen in the awesomely weird fossil reptile Charavipteryx, which, although incapable of powered flight, formed the bulk of its gliding surface with its hind legs while using its front legs as stabilizers, reminiscent of the canards on a delta wing aircraft. The flying elastospondylls may begin with a similar configuration of patagium before developing the musculature to generate the lift needed for true flight, becoming the first flying animals on the planet. To specialize for flight, their bodies will need to become more streamlined, and so their eye stalks and oral tentacles may shorten to reduce drag.
Looks like a flying Cthulhu monster, my guy. What did you do to it? It's a flying Cthulhu. Look at it. Look at it.
Efficient flying will also put a huge demand on their metabolism, as flight is a very high energy activity and requires a number of physiological adaptations to sustain. First of all, the lophostome's mechanism of passive respiration may not give them the high stamina needed for flying, especially with atmospheric oxygen levels declining.
15 hearts.
However, these flying elastospondylls may overcome this by exploiting a unique quirk of their anatomy. As they fly, the contractions of the posterior muscles will cause the gladius to undulate, which successively constricts and expands the lungs, pumping air in and out and providing them with more oxygen.
Ah.
This can be complemented by evolving specialized breathing muscles in the thorax, giving them a system of active respiration similar to that of the osteopods, and thus enabling much more efficient flight. This innovation may coincide with a change in their metabolism. All the animals we've seen so far are ectotherms, sometimes described as cold-blooded, meaning their internal body temperature is almost entirely contingent on the ambient temperature of their environment. However, the metabolic reactions needed for sustained muscular activity are most efficient at a consistent high temperature, which ectotherms can only achieve in sufficiently warm climates and by spending long periods of the day basking in the sun.
Bro, what the hell? This thing looks like a mini Godzilla. A little bit, don't it? Look at it. It's mini Godzilla. Why are you not attacking Japan? What are you doing over here chilling?
This constraint means that our elastospondylus will only be able to fly in short bursts if their body isn't suitably warm. So to optimize their flight performance, they may evolve some form of thermoregulation, the ability to modulate internal body temperature to keep it within a metabolically favorable range. Thermoregulation is often used synonymously with endothermy, where an internal temperature is almost always constant, only ever varying within a few degrees, as is done in mammals and birds. But some animals fall between the two extremes of ectotherm and endotherm, and thus sometimes get called mesotherms. For example, regional endotherms only maintain an elevated temperature within certain metabolically demanding areas of the body. Some clades of fish, like lamniform sharks and tuna, use countercurrent heat exchange between blood vessels to warm the areas around the eyes and locomotor muscles, ensuring they can function optimally even in cold waters. And many flying insects warm up their thorax by rapidly contracting the opposing muscles without moving the wing, generating heat in a similar way to the shivering reflex in mammals and birds. We'll discuss thermoregulation in more detail later, but something similar to the latter mechanism might evolve in the flying elastospondylus. Specialized muscles within and around the wing membrane may engage whenever the wing's temperature drops below a certain threshold, decreasing the reliance on warm environments for efficient flying, which combined with their active respiration will enable them to sustain prolonged periods of long-distance flight. As the first flying animals in the planet's history, these elastospondylus will have all the aerial niches to themselves, and so may be hugely successful and undergo an explosion of diversity, which we'll explore in future episodes.
What the hell is that even?
Let's call them Opisthophterans. Meanwhile, on the ground
so
below,
much.
the osteopods will need to find their own way to adapt to the changing landscape. One of the immediate pressures imposed by the steppe is that, without the cover of the forest vegetation, animals will be much more visible and vulnerable to predators, encouraging the evolution of new defensive adaptations. No longer bound by the dense forest vegetation, some herbivores, like the megalobrachids, may respond to increased predation by getting bigger, as a large size acts as a deterrent to attackers. Plus, it comes with the added benefits of an expanded feeding envelope, letting them feed on vegetation out of reach of other herbivores, and it acts as a method of thermoregulation by increasing the amount of body heat they generate. But attaining an especially large size requires several key adaptations. First of all, our old friend the square cube law means that doubling an animal's size will increase its volume, and therefore its weight, by a factor of 8, and to support this extra weight, the legs will need to become 2.83 times thicker. As the creature gets larger and larger, the legs will eventually become so thick that it will be impossible to maintain the enormous amount of muscular energy required to move them. Having a skeleton helps a great deal in increasing maximum size, as bones are much better at withstanding compressive forces than pure muscle. But optimizing the weight-bearing potential of these bones requires a change in their arrangement. Most of the osteopods we've seen so far have limbs that are splayed out to the side of the body, like many amphibians, reptiles, and arthropods on Earth. This sprawling posture provides a wide, stable base that reduces the chances of falling over, but it can't support a great amount of weight, although on our alien planet this constraint is slightly alleviated by the low gravity, such that the native fauna may support themselves with a more splayed posture than animals of equivalent size would need on Earth. But as the animal gets heavier, the most efficient way to support the extra weight is for the limb joints to move closer to the sagittal plane, or central line of the body, which reduces the amount of muscle power needed to stay upright and relieves the torque imposed on the joints. Beyond a certain weight, for the animal to be able to stand at all, the legs need to be positioned directly under the body and perpendicular to the ground. On Earth, this development occurred independently among archosaurs and stem mammals, which would later allow both groups to achieve immense sizes, So the same innovation might occur among the steppe-dwelling megalobrachids. Beyond the biomechanical constraints, a larger body also needs a greater amount of food, so an animal's maximum size will be contingent on the abundance of food in its habitat. This may preclude many of the larger species from colonizing the sparse inland regions towards the center of the supercontinent, but the areas along the edges of the coastal forests may be rich enough in vegetation to fuel the growth of the biggest animals yet to evolve. We'll call these giant megalobrachids titanopods. Once they're established as the dominant herbivores, different clades of titanopods may specialize for different modes of feeding. The forest-dwelling megalobrachids from which the titanopods descend were primarily browsers, using their elongated pedipalps to reach for high vegetation. One clade of titanopods may retain similar feeding behaviors, taking advantage of their enormous size to feed on the leaves at the very tops of the trees. And since no other clade can rival them in size, they'll have these browsing niches all to themselves. Free from competition, these forms, which we'll call proceropods, will thrive in areas where stands of trees grow alongside patches of open plains, such as gallery forests that grow around large rivers and lakes. But in areas with fewer trees, the titanopods will need to adapt to feed almost exclusively on the brachyphytes, and thus change their feeding habits to become dedicated grazers. These species won't need to reach upward for food, and so may have shorter legs and smaller pedipalps, indiscriminately stripping the brachyphytes to the ground like giant living lawnmowers. We'll call these creatures baropods. Together, the proceropods and baropods will dominate the niches of large herbivores, but the plains also offer niches for smaller, more adaptable animals. Although most platodonts are adapted to life in the trees, some of the more generalist species may be able to eke out a living on the steppe as the forests disappear, which may give rise to a clade of permanent ground dwellers, which we'll dub Edaphotheres. Just like the megalobrachids, the Edaphotheres will be more exposed to predators on the steppe, and so will need to invest in some form of defense. Competition from titanopods may prevent them from reaching large enough sizes to offer substantial protection, but the Edaphotheres can instead use their speed and agility to outrun their predators. Once again, though, sustained activity is most efficient at high body temperatures, so just like the Opisthophterans, the Edaphotheres may evolve a means of thermoregulation, perhaps investing in full-fledged endothermy to give them high energy levels throughout the whole day. However, endothermy does come with a drawback. A constantly high metabolism needs a lot of food to maintain. Whereas ectotherms, like crocodiles, can go for over a year without a meal, endotherms are required to feed much more often. Can go for over a year without a meal. Endotherms are required to feed much more often, with extreme cases like the American pygmy shrew needing to eat 3 times their own weight in food every day. Fortunately for the Edaphotheres, though, the steppe offers an abundance of food, and the adaptations they inherit from their platodont ancestors make them well equipped to exploit every available source of nutrients. The forest-dwelling platodonts had a varied diet of mixed plant matter in addition to malacoforms and other assorted small prey. One clade of Edaphotheres may remain adaptable generalists, but adopt 2 additional feeding behaviors. Firstly, scavenging. Carrion represents a rich source of protein to supplement their diets, so these Edaphotheres may therefore assist the
Bro, yeah. The picture on the left kind of looks like one of those pictures. Something should not be there. Find what should not be there. What is that? Is that a coyote? What is that? What is it doing over there?
Represents a rich source of protein to supplement their diets, so these Edaphotheres may therefore assist
when you go to the wrong party.
Necrophytes and malacoforms in keeping the steppe clean of carcasses. It's important to note that above a relatively small body size, relying on scavenging alone for food becomes impractical, since carrion rarely occurs in quantities sufficient for a large animal to live on exclusively, so most scavengers will still actively hunt prey if carrion isn't readily available. Scavengers often have keen senses to help them detect food over long distances, so in our Edaphotheres, the scent receptors lining their spiracles may expand into complex olfactory chambers with a large surface area to increase their sensitivity. To help them reach inside the bodies of carcasses, their pedipalps may become slender and gracile, tipped with taste receptors to probe for fresh meat, and a saw-like arrangement of serrated claws will help them tear chunks of flesh from within. Another feeding behavior these Edaphotheres might adopt is oviviry. Eggs are rich in essential nutrients, and the steppe will be littered with the oothecae of megafauna like the titanopods. In addition,
Okay, I got a question for all my smart boys that see this video. This snake, what does it do with the shell of the egg after it breaks it in its stomach? Is that shit not gonna cut it or something? Like, does it absorb it as well? How strong are these things' acid shits?
In addition to
Stomach
helping them
juices.
locate carrion, their powerful sense of smell may also assist in finding widely scattered nesting sites, even letting them detect eggs that are buried under several centimeters of soil. However, if their slender pedipalps are adapted for cutting and processing meat, they won't be very effective at digging, so to help them unearth buried eggs, the feet on their front walking limbs may become stronger and broader like spades. While still considered omnivores, these feeding behaviors may increase the prevalence of meat in their diet, and therefore most species in this clade will qualify as mesocarnivores, animals who gain between 50 and 70%
What is that? It's pretty cute. What's that? I've never seen that thing before in my
of their
life.
energy from meat and
that?
subsist on
Yep.
plant matter for the rest. Let's call these adaptable creatures Eurychirids. But the most plentiful source of food on the steppe is the virtually inexhaustible colonies of brachyphytes, which a second clade of Adaphithias may specialize to feed on exclusively. Their broad teeth, previously adapted to cope with a variety of mixed foliage, will make short work of the brachyphyte's soft, waxy leaves and spongy bulbs. And with sufficient food and the metabolic machinery for high levels of activity, these herbivorous Adaphithias can further invest in speed, possibly undergoing adaptations for cursorial locomotion. Cursorial animals are those that are specialized for high speed or long distance running, which is associated with a number of common developments. First of all, cursoriality is strongly correlated with an erect limb posture, like we saw in the titanopods, which not only allows the limbs to support a larger body size, but also to transfer more force to the ground for more efficient running, so our herbivorous Adaphithias may undergo a similar shift in posture. Secondly, cursorial locomotion is made more efficient by increasing stride length, or the distance between footfalls, which can be extended by making the limbs longer and increasing the range of motion of the joints. Luckily for the Adaphithias, they already have long, flexible limbs, used by their arboreal ancestors to climb trees and reach between branches, making them somewhat pre-adapted for cursoriality. Another way to increase stride length is to alter the posture of the foot. The foot structure of vertebrates on Earth can be broadly divided into three forms. Plantigrade walkers keep the foot flat against the ground, which provides stability and effective distribution of weight. Digitigrade walkers, on the other hand, walk on their toes with the heel raised off the ground, while ungulagrade walkers stand on the tips of their toes, which are usually elongated and adapted into hooves, which is why in many odd-toed ungulates, what looks like the lower leg is actually a single hyperextended toe. Cursorial locomotion favors the latter two forms, as they essentially serve to add the length of the foot to the stride length. While the skeletal comparisons between vertebrates and osteopods aren't exactly equivalent, these cursorial Adaphithias may evolve longer feet with only a single point of contact with the ground,
It's a
and their
horse.
hooked claws, once used for grabbing tree branches, may become blunter and hoof-like to give them purchase against the substrate. Finally, cursoriality benefits from an elongated, flexible spine. In animals like the cheetah, the spine can bend far enough forward for the front and hind limbs to overlap, which allows for the entire length of the body to contribute to stride length as the spine extends. The herbivorous Adaphithias may mimic this by evolving a longer, more flexible body with more space between the limb girdles. All of these adaptations will make these animals, which we'll
Wait,
call leptopods.
I don't understand. So he gave this thing hoofs like horse feet, but it gave it a cheetah spine. How is it gonna benefit from it? Like, look at the way it's structured. It cannot increase its stride like that, can it? I don't know.
Some of the fastest animals on the steppe, but they won't be the only animals to specialize for speed. With the plains accommodating such an abundance of herbivores, it's inevitable that new predators will evolve to hunt them. Before the climate changed, the Deinignathans were at the top of the food chain, but as the steppe spreads, the dense vegetation that they rely on for ambush hunting will disappear. Although they're easily large and powerful enough to hunt prey like the titanopods and leptopods, their great size makes them very easily spotted out in the open, so ambush tactics are no longer a viable option, and the fused, robust limb girdles they have in common with all Siniscians can't articulate very far, so they may be prohibited from specializing for cursoriality. Without the speed to keep up with fast-moving quarry, the Dynagnathans may not be able to adapt for predatory niches on the open plains, only surviving within areas of vegetation dense enough to conceal them. On the other hand, the dromaeopods have already evolved a limb orientation suited for pursuit hunting, and so are in some ways pre-adapted to hunt swift prey on the steppe. Like the leptopods, the active lifestyle of the dromaeopods may lead to them convergently evolving thermoregulatory mechanisms. But unlike the leptopods, whose activity levels remain more or less constant as they feed on the bountiful brachyphytes throughout the day, the dromaeopods will oscillate between periods of high activity when hunting and long spans of low activity between hunts. To make thermoregulation more economical, they may adopt another form of mesothermy. Facultative endotherms only regulate their temperature under certain energetically favorable conditions. For instance, hummingbirds have the highest metabolisms of all vertebrates, letting them power the extraordinarily rapid beating of their wings for extended periods. But when resting or in the absence of sufficient food, the energetic demands of thermoregulation are no longer practical or necessary to maintain, and so their internal body temperature plummets. Likewise, our dromaeopods may only thermoregulate when hunting for optimal performance, while between hunts or when food is scarce, they may cease thermoregulation to conserve energy. To augment their already impressive speed, the steppe-dwelling dromaeopods may undergo similar cursorial specializations to the leptopods, including an erect posture, elongated limbs, and a flexible spine. But they may gain a further advantage from one particular adaptation. All osteopods have one pair of pedipalps, used to sense the environment and to handle food, and 4 pairs of walking legs, inherited from their sarcopod ancestors. Among terrestrial body plans on Earth, the number of limbs present is wildly variable, ranging anywhere from 0 to multiple hundreds. While the minimum number of legs needed for a cursorial animal is only 2, having additional legs increases the animal's stability by creating a wider base. However, extra legs require extra energy to maintain the necessary musculature, with diminishing returns for every additional pair of legs. On Earth, terrestrial megafaunal niches are exclusively occupied by vertebrates, almost all of which have 4 limbs, so it's difficult to know how viable a large cursorial species with more than 4 walking limbs would be, but it seems likely that to maximize speed and minimize unnecessary energy expenditure, the steppe-dwelling dromaeopods may evolve to run on only 6 legs rather than 8. Initially, these dromaeopods may use their frontmost pair of walking legs along with their pedipalps to catch and restrain prey. Over time, these legs may lose their locomotive function entirely and be held permanently off the ground, giving them the freedom to be secondarily adapted to aid in manipulation, as happened on Earth in animals like mantids, dinosaurs, kangaroos, and australopithecines. Geert van Dijk, author of the blog on Forahan Biology and Allied Matters, has coined the elegant term centaurism to describe this condition. From here, the limbs may become clawed arms to latch onto fast-moving prey, while the pedipalps may sharpen into fang-like points to deliver the killing blow. This innovation will simultaneously give them the speed and maneuverability to keep pace with the leptopods, and the weaponry to tackle prey as large as the titanopods. These specializations may go along with a shift in diet. Unlike the more generalist eurychirids, most of which are mesocarnivores, some of these steppe-dwelling dromaeopods may evolve into hypercarnivores, animals that obtain over 70% of their energy from meat. This suite of new adaptations will make these dromaeopods the top predators of their day. I'll call them ornicodonts. All of these clades represent only a tiny fraction of the diversity that the steppe will support, but they'll comprise the most populous and successful groups over the 30 million years or so following the retreat of the global forests. But away from the equatorial plains, the disruptions in the planet's climate will have far greater ramifications, felt not only on land, but also in the ocean. In the next episode, we'll see how some of our terrestrial species exploit the newly vacated aquatic niches and undergo the unprecedented transition back into the water.
Oh shit, getting
Thanks to
kicked out of the
Campfire
land.
for sponsoring this episode. If you've got your own...
Hey, that was awesome. That was awesome. I'm excited for the next episode. Seems like some crazy shit's about to happen soon. Mass extinctions. New evolutions. The world shall never be the same again. Anyway, let me know what y'all think. As I've said in the other videos, we have a Discord channel. I'm gonna be streaming some Fable, probably like 30 minutes after the video gets uploaded. And I'll see you next time, everybody. Have a nice day. Bye bye.